Okay, to solve this problem, I think there are a couple of ways to do that. I can think of two main ways. One is simply to just use storage system, okay, and the other is to use hybrid renewable energy system. When you use, I think engineers prefer the hybrid renewable system because it gives this flexibility for optimization and all of that. Okay. And when we say talk about hybrid renewable energy system, we're talking about using different energy sources to supply load. Okay. And when you have these different sources to smoothen these renewable sources, okay, to supply load, you have the issue of scheduling. Okay, how do you manage this component to effectively, okay, and meet this load and all of that? So the focus of our thesis of my work was on this energy management. Okay, this our work is actually on the high level control of these different sources. We're not looking at the low level voltage, frequency, signalization control. We're looking at the high level scheduling. Okay, and you see in this picture that the strategy you use to build your hybrid renewable system depends affects the component size. Okay, the component sizing is a function, it's a direct function of the strategy you use. Okay, and and of course, if the component size depends on the strategy you use, it tells you that the cost of energy production will depend on the strategy you use. Okay, so there's need to do more research in this area and all of that. There's need to get the reasonable dispatch algorithm or EMS. Okay. So in literature and in the industry, there are basically two extremes of this EMS. Okay, I'll be calling it dispatch control. Okay, the technology is very mature. There's lots of algorithm and technology in the industry on this. Okay, there are two extremes. We have the industry standard and the academic frontier. Okay, in the industry standard, there are basically conventional dispatch algorithms. They are very simple, logic rule-based algorithms. They are practical to implement. They're very easy. They're practical, very easy to implement, and they are commercially deployable. Okay, but they have this limitation because they are very rigid. Okay, they don't see far at all. Okay, they're very myopic, and they're majorly suboptimal. Okay, while on this side, on the academic side, the theoretical optimization side, we have the MPC, the linear programming algorithm. We have the Metaheuristic guys like the GA, the PSO, and all of that. They have this. They are mostly mathematically optimal. Okay, they balance the computing objectives. Okay, but the limitation is that you have computing objectives, so they're very complex to model and all of that, and they are difficult to deploy real time. They could be very beautiful on paper, but deploying it real time is uh, is difficult most of the time. So what we're trying to do is to like a bridge, like a common ground between the two. Okay, build something that is nearly optimal. Okay, and that can be implemented real time. Okay, practically. Okay. So this brings us to the problem statement and the motivation of this work. The conventional dispatch they are myopic, and at best they are suboptimal. Okay, yielding about 15 to 25% higher unit cost than is theoretically available. While the MPC guys are mostly impractical, okay, they're very complex to implement in real time. Uh, it's popular in the industry that MPC is very complex and expensive to implement. Okay, and the traditional Metaheuristic guys are very most of the time slower to converge, and they still have this problem of real time implementation as well. Okay, and we've seen the motivation. We've seen that the sizing of our hybrid system depends on the dispatch used. Okay, so there's need to get something that is nearly optimal that can make flow heuristic algorithm. It's developed in 2024. It's got from literature. It's to develop this framework for hybrid system by combining the SEMPA MPC optimization linear regression surrogate modeling, and Homer Pro simulation. This is our objective: to develop a framework, to train a regression model, deploy it in Homer, and when we deploy it in Homer, Homer has three basic how do I put it? Homer has three basic fundamentals. Okay, one is for simulation; it gives you environment for simulation. The second one gives you the ability to optimize your component and all of that, and it gives you the ability, environment for analysis, sensitivity analysis, and lots of all of that. So we're going to use Homer to evaluate our framework and compare with conventional dispatch algorithms. Okay, as I mentioned, that dispatch algorithm and control is actually a very mature topic in literature. So there are lots of them. This is just a summary of few of the literature got and how it relates to our work. Okay. So the identify research gap is basically tied to the problem we discussed earlier, the problem statement we discussed earlier about the practicability of MPC and the suboptimal of the conventional sources in the future. So our proposed solution is to develop this framework where we generate optimized operating trajectory offline using SEMPA MPC. We transfer the intelligence of this optimization using regression models, okay, and we link this to Homer as a custom dispatch and run our analysis. Okay. So this is the main contribution of our thesis, a novel SEMPA MPC ML pipeline for hybrid optimization, the open source Homer Pro custom dispatch model, and prove that this framework achieves lowest cost of energy and at the same time meets load and all of that. Okay, this is the methodology we're using. Firstly, we're using SEMPA optimization to give us optimal sizing of our hybrid renewable energy system. Then we use our MPC control to generate trajectories. Okay. We use our linear regression modeling to copy the intelligence of this guy to simple-based algorithm that is implemented in Homer. Okay, and we run our simulation analysis in Homer to compare the conventional dispatch algorithms. Okay, for our system, these are our case study hybrid system we're using. Sorry. Okay, a simple hybrid system combining two buses, the AC and DC buses, combined together by this bidirectional converter. Okay, you see, to make our optimization problem very simple, we split the part from PV into two parts, and the generator comprises two parts, one to load, one to the battery. Okay, so that's what to make. And our case study is in Dammam here, and this is some of the weather parameters used for our case study. Okay, so we move straight to the sizing. Okay, we run our cost function for the sizing, we run our cost function on cost of energy, the total net present cost, and the ability of the component you get to meet load at every given time. Because we use the weather condition, we use the weather forecast for our case study and the load profile for case study to do this. And what are we looking for? The capacity of the PV, the generator, the battery, and the converter. Okay, this is what we need. This is just a deeper breakdown of our. Okay, the replacement cost is kind of very tricky because it depends on the generator hours run. Okay, it's very tricky. So we use this to get that. And the replacement cost too is very tricky because it depends on the generator hours run. In this case, it's 15 hours, 15,000 hours. Okay. Okay, we use four algorithms to solve our solution problem, starting problem. We use popular GE and PSO, and the recent marine predictive algorithm and the SEMPA, as mentioned earlier. This is just a flow chart of this graph. At the end of the day, in our work, you see this and Y. We use SEMPA for our sizing. Okay. In the results section, I'll show you where we use this. This is just the pseudocode of the SEMPA guy, and this is the flow chart of the SEMPA guy. Okay, our MPC problem formulation. You see, in the first part, for the sizing, we build our cost function around size and ability to meet load. In the second part, in our MPC problem, we build our cost function on technicalities, okay? Ability to control excess charging and discharging, ability to reduce containing power, and ability to reduce. You see, for batteries, storage system, are basically two degradation in battery system. We have the calendar and the cycling degradation. For the calendar one, when you have the battery still charged for a long time, it increases the battery. And when you have rapid charging and discharging, it decreases the battery too. So we're trying to this difference change in state of charge, trying to discourage the rapid charging and discharging by this staying in one place, dwelling in one place. So we are trying to discourage that. Okay. Why this is to reduce to penalize curtailing of our PV because in some cases you have cases where your the PV power is more than the load and the battery is charged. Okay, so we are trying to discourage that. None of that. So this is to do that, and we are discouraging the use of generator as well. Okay, in the case the reason is obvious to reduce fuel consumption and all of that. Okay, and of course we got our sizing from the previous optimization, and what we need is this guy. Okay, this is what we need. This is the trajectory we need, the PV use, the generator power output use, the net battery power use, the curtailing power, and the state of charge. Okay. It is like a schematic diagram of MPC. And this is the way to use for optimization. You got this from literature. Because this weighting, modeling this weighting is another skill entirely. Okay? It's another skill entirely. But for the sake of our work, we use this one. This guy is called from literature. Okay, the machine learning part to build our surrogate model. The idea is to get a function of the battery output and the DG output. How they depend on this guy's load, the PV available, the PV used, and the state of the charge of the battery. Okay, and to build the battery output as a function of these guys. Okay, for this is how we train our guys. We use 70% for training, we use 15% for validation, and 15% for testing. The metrics we use is our coefficient of determination, root square mean, and mean of absolute error, and our mean of absolute. Okay, and we use this for machine learning algorithms, linear regression, the regression tree, the support vector regression, and the posted ensemble. Okay, we basically use we implement this similar. So we at the end of the day use linear regression, and the reason because linear regression gives us a ready coefficient that can simply that'll be very relevant to our problem we're trying to solve. Because most of them very simple. Something more like a rule-based solution that have the intelligence of the optimizations done earlier. So this will do. Okay, so from the regression model box, we design our dispatch algorithm. Simple if test statement rule-based algorithm that will serve as a custom dispatch in Homer. We link it to Homer using our Homer MATLAB link, and this is the flow, like the flow chart for this dispatch. Okay, for the first part of our method, methodology, that's the sizing part. This is what we got. You see, SEMPA converges test, and that's what we settled for it. And this is at the end of the load is met 100%. That's the renewable fraction we got and the cost of energy we got from our SEMPA. This is the sizing we got from that and other metrics. So lack of time, I'll just rush through this. For our MPC result, this is what we got. This is how the various components of our hybrid system met the load, contributed to meeting the load. These are some of the time series trend and all of that. Okay, this is basically the trajectories using running our regression model. Okay, for our surrogate modeling, this is the result we got. For the metrics and all of that. Yes, this guy, the support vector guy is the best, but we settled for the linear regression because the difference is not much. Okay, that guy is easy to implement. So when we go as a regression model, we build our dispatch algorithm, link it to Homer to run our simulation. Okay, we got about 700 feasible solutions. Okay, so to get the optimal one, looking at our criteria, we run a Pareto analysis. Okay, to get the compromise. Okay, by the end of the day, this is what we got. This is the solution we used for our problem. Okay, so this is okay. And in our Homer simulation, we use the size of the generator, and we use the size of the generator, use our dispatch, and we left other component sizing to Homer to try to optimize as well. Okay, to give us the feasible cost and all of that. So this is what we did. So this is the size of the generator we use. Is what Homer gave us. Is the cost of energy. Is the renewable fraction, and the moment load is about 0%. Okay, this the part looking into the Homer results is how the various components contributed in meeting our load. You can see PV is dominant compared to the DG guy, and this cost component and all of that. And this is how the trend is to meet the load. Look at this guy, which is a sum total of these three guys is identical to those. Okay. This is the generator behavior by the year, throughout the year and with that. This is the PV behavior throughout the year. Okay, at the end of the day, we run a comparative analysis between our dispatch algorithm and conventional Homer input algorithms. Okay, so this is what we got. For cost of energy, our algorithm gives us best, the least. For American load is about 0%. It's quite small. For a renewable fraction is just second to a load following. And then we run a sensitivity analysis using this. The renewable fraction is quite insensitive to diesel price. While for the cost of energy, it's kind of in between, not very sensitive. Okay, and the good thing is that the cost of energy is lowest among the four. Okay, for net load, the sensitivity is kind of highest, one of the highest, but it's still within reasonable threshold. Okay, we run an sensitivity analysis using the load variability. Okay, what load variability means is for every 24 hours, in our case, okay, we made it 24 hours. For every 24 hours, the load changes. Okay, So this is the percentage of the load changes by 5%, 10%, and okay, we ran that and check the algorithm. So this is what we've got. This guy is very insensitive to it. The load, the cost of energy, as you can see, is the best among the four. The unmet load too, it's kind of very sensitive, very sensitive, but it's still within acceptable range. So the last time I met Dr. MD, he insisted I use our framework to look at existing work in the literature, and he mentioned I used energy to be precise. So I tried to do that. I tried to reproduce this work. This guy is just take conventional algorithm, the state of charge, the cycle charging, the load flowing, and combine dispatch. So I use our framework to try to reproduce this, and this is what we got. The cost of energy is the best among the four. For met load is second best to load following. Second best to load following on the graph. So in conclusion, we see our developed framework establish a bridge between the Metaheuristic sizing, predictive control, machine surrogate modeling, and human-based assessment. The battery was able to transfer most of the intelligence. If you look at the cost of energy of the MPC and of the human, they are quite close. Like for the MPC is around 0.188, while for the human, one of us is 0.172. Quite close. And the proposed framework successfully integrated the human probe, produced this solution. And the MPC guy, compared to other guys, is optimal. Okay, because he has the lowest cost of energy and all of that. So for future work, this is a recommendation for future work to impose on method as a hard constraint or increase outage penalty to improve reliability and varying conditions. To investigate non-linear surrogate models. In our case, we use linear regression model. And I think we can look deeper using like this vector guy to improve how the intelligence is copied to Homer and all that. And we can extend our architecture to include PV, hydrogen system, and demand response capabilities. Okay, we can apply our framework to multiple areas. Of course, I did that, but it's not reported here. I tried our framework, besides using the paper, trying the published work. I use my location in Nigeria. It still gives it still gives the best in terms of cost of energy and meeting load. Okay, we can model forecast errors in load and give the ratio of a partial online MPC implementation. We can validate the framework experimentality on the physical microgrid of hardware in the load platform. These are some of the references used for the work. Acknowledgements. First of all, I would like to thank God Almighty for His mercy. I think if without the mercy and grace of God,